Hello everyone. Welcome back to the Introductory Physics series, and today we are going to delve deeper into the topic of using and converting units. For this video, I'm going to use a little help from our math expert, Liz, because she is a master unit converter. Now, last time we began talking about the importance of units in physics, but one of the many reasons units are so important has to do with their role in physical equations. For example, if we look at a familiar equation, speed is distance over time, where here the algebraic symbol v represents speed, d represents distance, and t represents time, each of these algebraic symbols inherently carry a number and also a unit. So, for instance, d might represent a distance of 600 miles, t might represent a time of 10 hours, and correspondingly, v might represent a speed of 60 miles per hour. In each of these cases, the algebraic symbols carry both a number and a unit. Just saying that d is 50 or t is 4 without quoting a unit is just simply meaningless in physics. Because physical equations carry both numbers and units, the equal sign suggests that both the number and the unit must match up on the left-hand side and the right-hand side of the equation. So, taking our previous example, if d is 600 miles, t is 10 hours, and v is 60 miles per hour, the left-hand side of the equation is 60 miles an hour, and as expected, the right-hand side of the equation also reduces to 60 miles an hour. So we know that this equation holds. I want to emphasize in particular here that the equation has the same units on both the left-hand side and the right-hand side of the equation. Or in other words, the equation is dimensionally consistent. So v is d divided by t is a dimensionally consistent equation. On the other hand, the equation d is v divided by t is not dimensionally consistent. Using the same units as before, on the left-hand side we get miles, but on the right-hand side we have miles per hour divided by hours, or miles per hours squared. And since the units don't work out, we know that the physical equation must be incorrect, or in other words, it is once again dimensionally inconsistent. As the saying goes, we cannot add apples to oranges. So, in physics, it is extremely important to check that your equations are dimensionally consistent at all times. What that means is that you should always carry your units when solving physics problems. Remember that every algebraic symbol carries a number and a unit, so don't forget to write those units down. That way, if you ever encounter a dimensionally inconsistent equation in the middle of solving a physics problem, you know that you've made a mistake somewhere. Trust me, in terms of solving physics problems efficiently, carrying units really pays off.
Alright, so now that you know how to use units, let's talk about how to convert them. Unit conversions play a big role in keeping equations dimensionally consistent, and in a lot of real-life situations, it's likely something you do without even thinking about, like swapping between days and weeks, or minutes and seconds. However, it is important to understand how to perform unit conversions formally, even simple ones, because it will help build the foundation for working with more complicated units later on. We begin with the familiar example of converting from minutes to seconds, since as we learned in the last video, seconds is the most fundamental unit of time. Suppose we need to know how many seconds are in 3 minutes. Now, I wouldn't be surprised if you could tell me right off the bat that this is the same as 180 seconds. But like I said, it's important to be able to formalize it and write it more mathematically. To do this, we start with the fact that 1 minute is equal to 60 seconds. To convert 3 minutes into seconds, we take 3 minutes equals 3 minutes times 60 seconds divided by 1 minute, since that 60 seconds divided by 1 minute is the same thing as 1. Canceling minutes from the top and from the bottom of the right-hand side, we're only left with the unit of seconds, and then we know then that 3 minutes is equal to 180 seconds, just like we would have expected. Sometimes, Writing out small conversions like this may seem a little bit silly, but it's an important process to have later on.
For our second example, let's take a look at a conversion between units of length. Although we rarely use the imperial system in physics, it doesn't hurt to get some practice converting from imperial units to SI units. So in this example, we will convert inches to meters so that you can tell all of your international friends what your height is accurately in meters. For this, we need the conversion factor that 1 inch is 2.54 centimeters, and the knowledge from our previous video that a centimeter is 100th of a meter, so 100 centimeters is 1 meter. Okay, so for instance, if we have 15 inches, we can string these conversion factors together and write that 15 inches is equal to 15 inches times the first conversion factor, 2.54 centimeters divided by an inch, multiplied by our second conversion factor, 1 meter divided by 100 centimeters. We see that all the units cancel except for the meter, which is exactly what we want. And punching the numbers into the calculator, we get that this is 0.381 meters. So there you have it. If you apply the same technique, you can find out how tall you are in meters. How cool is that?
Our next example incorporates the conversion factor we used in the last example and applies it to a slightly more involved situation. Volume. Suppose we want to convert from 10 inches cubed to centimeters cubed. Again, we start with the relationship that 1 inch equals 2.54 centimeters. Now, it may be tempting to go straight to taking 10 inches cubed equals 10 inches cubed times 2.54 centimeter divided by 1 inch equals 25.4 centimeters cubed. But we can't do that. Why not, you ask? Good question. This is because, again, we want to think about the conversion factor canceling out the existing units. But we didn't manage to do that completely this time because inches cubed is the same thing as inch times inch times inch. That's 3 copies of the inches unit, but our conversion factor as it was only accounted for 1 of them. So we must substitute in 3 copies of our conversion factor, or more simply, do the same thing to the conversion unit that was already done to the inches. Raise it to the power of 3. This means that what we really want is 10 inches cubed equals 10 inches cubed times 2.54 centimeters divided by 1 inch, all raised to the 3rd power. Everything inside of the parentheses gets cubed, in particular that 2.54. We then cancel out the inches cubed from the top and the bottom, leaving just the centimeters cubed, and we get 163.9 centimeters cubed. We can also check to make sure that this makes sense physically, since we need some unit cubed to express volume. We started with inches cubed, and we ended with centimeters cubed. So I think we've done pretty well.
All right, in our final example, we work with units for speed. In daily life, we typically talk about miles per hour for speed, but in physics, we like to work with meters per second. So I will show you an example of how to convert 50 miles per hour into units of meters per second. This example is different from the others because it works with 2 distinct fundamental quantities, distance and time. Because of this, we will have to apply 2 separate conversion factors, one for miles into meters, and the second for hours into seconds. And the easiest way to do this is to apply them both at the same time in a chain. So let's get started. First, to convert from miles into meters, we need the conversion factor that 1 mile is equal to 1,609.34 meters. Now, to get seconds from hours, we need to convert hours into minutes and then minutes into seconds. The easiest way to do this is all at once, much in the same way we will convert miles per hour into meters per second. We, first of all, know that 1 hour is 60 minutes and 1 minute is 60 seconds. So we can apply both of these at the same time to 1 hour. So 1 hour multiplied by 60 minutes divided by 1 hour, and the second conversion factor, 60 seconds divided by 1 minute. So notice that everything cancels out except for the second, leaving us with 3,600 seconds if you plug that into a calculator. So we are now ready to convert 50 miles per hour into meters per second. We will use both conversions. 1 mile is equal to 1,609.34 meters, and 1 hour is equal to 3,600 seconds, giving us a chain. 50 miles per hour is 50 miles per hour multiplied by the first conversion factor of 1,609.34 meters divided by 1 mile, and the second conversion factor, 1 hour divided by 3,600 seconds. In this string of units and numbers, all of the miles and hours cancel out, leaving us with just meters on the top and seconds on the bottom. So simplifying all of these numbers and units, we get 22.35 meters per second. This technique of stringing together unit conversion factors is what you will want to use anytime you convert more involved derived units like speed and weight, among others, because it helps you make sure that you have applied all the conversions that you need to.
All right, so today we talked about using and converting units. We learned what it means for an equation to be dimensionally consistent and discussed how always carrying units is the way to go to ensure that your work is dimensionally consistent when solving physics problems. Then, we talked about converting units and walked through 4 common examples ranging from easy to more challenging: units of time, length, volume, and speed. If this was your first time you've formally dealt with units, or it has been a while for you, we encourage you to get some more practice using and converting units, since units are only going to get more complicated as you continue your physics journey. And with that, see you next time when we will discuss uncertainties and significant figures.